Hello, my name is Devin Sella. Today I'll be talking to you about my project I did with iSono Health, which is a small startup in San Francisco that's trying to make breast cancer screening more affordable and interpretable for patients. In the US, 1 in 8 women are diagnosed with breast cancer during their lifetime. In 2019, more than 40,000 will die. Most of these deaths are preventable because if caught in an early stage, breast cancer is highly treatable. We need a tool to help make doctors more efficient and help them prioritize, because at this point they have to see something like a new image every 8 seconds for their full working day. And this is only going to get worse as more and more data is collected for each patient. This is where I come in. I implemented the back-end lesion detection tool that would go into iSono's device. So iSono has a portable 3D ultrasound, but they don't have very much data from their own device at this point. Instead, I was given a proxy dataset from 2 different data sources. One is primarily primarily video. It's from a fewer number of patients. And the rest are from an academic source and are only pictures of lesions of different subtypes. So I already had a strange patient imbalance. The actual class balance, if you add up all the images, is not too bad, 58% abnormal for overall. I made sure that my train test split had the same class and slight class imbalance, and I also made sure that a single patient that had a video, for instance, was not partially in the training set and partially in the test set, so I didn't have any data leakage. So because this was a proxy data set, I wanted iSono to be able to evaluate new models as they collected more data. So in this case, I implemented a model testing pipeline for them. So data was all processed using OpenCV. So this includes cropping as well as putting to grayscale and normalizing the images. Training was all done using PyTorch pre-trained models, including from PyTorch Model Zoo, PyTorch Hub, and newer implementations of different algorithms found on GitHub. But the training data was heavily augmented using the Engage Python package. And this is just because I have a very limited data set. I want to make the most of it, make my algorithm very robust. The hyperparameters were optimized using Axe, which is Facebook's new Bayesian framework that can be used for, among other things, optimizing hyperparameters. So the nice thing about this is I can set constraints, for example, on the inference time or the accuracy or the model size, as well as looking at actual just accuracy. And this is important because eventually they want their model to run on a mobile device or a local computer for a patient, which might be very old and has to run quickly. So at the left, you can see a nice little heat map of weight decay as a function of the learning rate, and the color bar is indicating the area under curve or AUC metric. So it's not very good in this one example, but you can see that as data points are picked, it slowly gets more and more to finding the actual optimal location for this model. So optimization was done after initial training, and then to help iterate on that training. Results were all logged using TensorBoard, which is something that they were already used to, and visualizations are created using GradCams, or gradient-weighted class activation mappings of we're looking at the last convolutional layer and seeing what it sees right before it classifies. In this case, this is a lesion classification. So 2 lesions are identified, the skin is identified for the subcutaneous layer, and the bottom artifact is an artifact and meant that I had to go back to pre-processing and fix my mistake. So this was being used in classifying as a lesion, and it was difficult to see in the grayscale image, but there's a very slight black border on the very bottom of the image. And because this is PyTorch, the code can be easily serialized and put into production quite rapidly. So for each model now, iSono can look at the relevant metrics that they care about and make a decision on what they want to use. So for one example, this is just the Inception V3 convolutional neural network, AUC of 0.93, and then this will process an image data set in less than a minute. A radiologist, it will take around 20 to 30 minutes. And I just want to also say that we want to be right up here with a high true positive rate for medical imaging, because we want to make sure that a patient who is diagnosed as normal is normal and does not actually have a malignant tumor. We want high recall. Lastly, a little bit about me. My work was all looking at lithium-ion battery materials, so the same ones that go into Tesla's car batteries. You take a 3D diffraction pattern and have an iterative algorithm that goes from reciprocal space to real space, and then create a real space image in 3D of a nanoparticle. And this is my cat to the right. Thank you for your time.